Hello everyone. So in this video, in this problem, we have sort of a different type of a sequence. So the nth term of the sequence is nth root of 3, and we want to show that the limit is 1. We want to actually prove it. So let's start. For any epsilon greater than 0, okay. Let's take the difference between the nth term of the sequence and the limit. So we want to find the n, okay, that large enough to guarantee this relationship. We want to actually find the capital N here, right, to match with our definition. Perfect. Now what can we do from here? Well, we can drop the absolute value here, okay. So because difference between these two expressions, difference between the nth root of 3, no matter what n you have, n is positive, okay, positive natural numbers, and difference between the nth root of 3 and 1 is always going to be positive, always going to be a number greater than 0. Now why is that? Well, think about this. Nth root, so nth root of 3, no matter what n you have, n is positive again, it's always going to be a number greater than 1. Okay, the common sense here is like think that the nth root is less than 1, so it's something like 0.9 or 0.8. so it's when you multiply a number less than 1 by itself several times, you will be not able to create 3, okay. You will get a number less than 1, okay. So for example, 0.9 times 0.9, if you multiply, you won't be able to get a number greater than 1. When you keep on multiplying, you won't be able to get a number greater than 1, right? So it has to be greater than 1, otherwise you will be, so think about this. So 3 is the nth root, means some kind of a number, okay, some kind of a number multiplied by itself n times, right? So that's the, so a is the nth root of n. So the idea here is if you multiply a n times, you should be able to create 3, right? But if you have a number less than 1 as a, as the nth root of 3, you won't be able to create 3, okay. So I hope that it makes sense. So this is positive. Anyway, we are working with positive. We can, if it is negative, we can drop because we have absolute values, okay, but it's not negative. Anyway, the difference is not negative, okay. Perfect. Now what can we do here? Well, for a start, we can take 1 to the right hand side, so it's going to be epsilon plus 1. Now what we can do here is, well, let's see. So this is 3 to the power 1 over n. I rewrite it in a different manner. Now let's take the natural log of both sides. So natural log 3 to the power 1 over n. Oh, it's epsilon plus 1. Where did c come from? Natural log epsilon plus 1. So this is the trick, okay. Here the goal is to make n subject, I mean not the subject, to isolate him, right? We want to isolate n. So here 1 over n comes out. That's the logarithmic properties. Hopefully you can remember logarithmic properties, which is if you have something like natural log ab, we can write it as a to the power b. We can take that b in front, we can write it in front of natural log, okay. All right, so I use that property. Now from here it's rather easy, right? Okay, so we know epsilon is greater than 0, so whatever, so natural log of epsilon plus 1 is always positive, natural log of 3 is always positive number. So we can switch the sides of let's see, natural log 3, let's bring natural log epsilon plus 1 to the left and take that n is always positive, so take that to the right hand side and the inequality doesn't change, okay. All right, so this is the relationship. So I can write n is greater than n natural log 3 over natural log epsilon plus 1. Perfect. Now this is your capital N, okay. It's a positive number if you are worried, okay. Great. Now all what we need to do is write down our proof formally. So let's write the proof. Let epsilon greater than 0 and let capital N be what we found, natural log 3 over natural log epsilon plus 1. Perfect. And then simple n greater than capital N implies simple n greater than natural log 3 natural log epsilon plus 1. So from here we have to work backwards. Okay, so backwards in our scratch work. This implies we can say where did we go? So from here we can say natural log 3 over n is less than natural log epsilon plus 1, right? So that is where we got this expression from. Okay, so this implies we can say using logarithmic property inversely we can say this, right? And we can drop the natural log sign and we get this relationship. This implies. All right, now here we can take the 1 to the left hand side, and of course from this we can say, because it's always positive, so it's not necessary for absolute value, but for the sake of the definition this is what we get. All right, so it perfectly match with our definition and it works. So hence this proves limit. Okay, so we have, if we have a sufficient if we have n following this relationship, it guarantees this expression. So that means the limit of 3 to the power 1 over n is actually 1. Okay, all right, so we proved that. All right, hello everyone. So we have another sequence here and we want to prove that the limit of this sequence is half. Okay, so let's start our scratch work. All right, so for each epsilon, so for any epsilon greater than 0, let's take the difference between the nth term of the sequence and the limit. Okay, so we want to find how large simple n should be in order to guarantee that this distance is less than epsilon for each epsilon. So we want to know how large this simple n should be. We want to find the capital N, right, that match with our definition of the convergence of a sequence. Perfect. So let's simplify what we have inside this absolute value. The common denominator is going to be 2 times 2n square plus 3, right? And this will be 2 times n square minus 1 minus 2n square plus 3. All right. Now I would be careful with this negative here, the subtraction here. Perfect. Now let's see what's going on. If you simplify the denominator, let's keep it like that. And this will be 2n square minus 2 minus 2n square minus 3. So 2n square cancel out, right? This should be less than epsilon. So minus 2 minus 3 is actually, so this is minus 5 over, let's distribute 2. So it's 4n square plus 6. All right. Now the purpose of the absolute value is to get rid of the negative. So since we are only considering about all the positive values, we can consider 5 over 4n square plus 6. So we use the absolute values. Okay, absolute value notation. Right, because we use the because we take the absolute value of negative 5 over 4n square plus 6, that negative doesn't matter. Okay, now here we want to find a fraction that is easier to work with rather than what we have here right now. Okay, so let's think about this. Now the smaller the denominator, bigger the fraction, right? How can we find a fraction bigger than what we have right now and it's enough to work with this epsilon? Well, we can keep the numerator, it's just 5. Well, let's get rid of the 6. If you don't have 6, if you have just 4n square, definitely 4n square is smaller than 4n square plus 6. So when you take the reciprocal, 1 over 4n square will be bigger than 1 over 4n square plus 6. Well, 5 doesn't matter, so even though we have 5 in the numerator, the same relationship holds, right? So let's bound that by epsilon. So if this is sufficient to bound 5 over 4n square plus 6 by epsilon. Okay, that means 5 over 4n square is less than epsilon, of course 5 over 4n square plus 6 is less than epsilon. Okay, because of the relationship here. Let's work with this new inequality, 5 over 4n square less than epsilon. Let's switch 4n square and epsilon, shall we? So it's going to be 5 over 4. Let's keep 4 on the left hand side. N square. We can rewrite it as n square is greater than 5 over 4 epsilon. So let's take the square root. We don't need to worry about negative aspect of the square root because we are working with positive values here. N is positive. Okay. All right. Perfect. Let's make some space here. Now we have found the capital N. So the capital N that depends on epsilon is 5 over 4 epsilon square root of that. Okay, so let's write the formal proof here. Okay, so arbitrary epsilon, let epsilon greater than 0 and let capital N be, okay, let capital N be square root 5 over 4 epsilon. Then n greater than capital N implies, simple n greater than capital N implies 5 over, so we can replace capital N by what it is. Then we can take the square of both sides. So n square is greater than 5 over 4 epsilon. Okay, so we are basically working backwards of our scratch work, right? Now from here we can say epsilon is greater than 5 over 4n square, and from here we can say 5 over 4n square plus 6 is less than 5 over 4n square, which is less than epsilon. And let's find space. Shall we do the proof? Okay, here. All right, so let's continue it there. Now this implies absolute value of 5 over 4n square plus 6. We are working backwards, right? My is less than epsilon. Now this implies, okay, this implies what we started with, right? N square minus 1, 2n square plus 3 minus half is less than epsilon. So hence this proved that the limit of n square minus 1 over 2n square plus 3 is actually half by the definition. Okay, all right, so that's the proof. That's how we prove for this particular sequence the limit is half. Thank you.